Now, before doing that, we actually want to lay down our camera animation first, because we want to know where to put those rocks in a way that they are framed by our camera, and also because we want to optimize our environment. You can imagine that will be a relatively high density mesh. By doing the camera animation first, we can actually use some proxy version of it where the camera is not going to look. So the thing is, the camera animation is driven by the core animation. So without going into the modeling or texturing of the core itself yet, we are going to lay down the basic animation for the core, then for the camera, so we can have an idea where to place our next rocks. As you can see from the final footage, the core itself is just a fancy icosahedron and the animation is pretty simple. The core rises up from the platform, it opens up, revealing the particles, then after a few seconds it will close and it falls on the ground. So this entire animation, it lasts 350 frames, so on the left lower corner of your screen you have the animation option. So here we can set the time range from 1 to 350 and also set your correct FPS value. I work at 25 FPS. So let's apply those settings. Now we have our full animation range. So before creating the core animation, let's go inside the rocks RNDR, and I want to move this rock a little bit. This rock is still at its original position, so let's plug a transform node after it, and I will plug the value I have on my scene, but just realize those are not magic numbers, these are the result of my R&D on the scene itself. You have to play with the values to find the result you are looking for. If you just want to follow the tutorial, just plug minus 1.6 for the x-axis and minus 3.65 for the z-axis. So this is my final position for this rock. Now let's go outside and create another geometry container that will be our core. Inside, drop down a platonic solid node and set it as icosahedron with a radius of 1. And also click here and set show all object so we can see our rock platform. Now drop down a transform node and plug it to the solid. For the animation, I already know that I want the core to be at its highest position by frame 50, so on frame 50 I will set the Y translate axis as 10 and I will alt and click to set a keyframe. When you see green, you have a keyframe in that channel and you are on that particular frame with the keyframe. Now back on frame 1, I want the core to touch the ground and I already know that the core value in my case is 5.1, so I will set another keyframe here. So the core is rising and I also want to fix this compenetration issue, so on frame 1 I will set my rotation X of 10.5, set a keyframe, and I want this also to be 0 again when the core will rise, so 0, and set another keyframe. So now we have the core rising correctly. Now the core should open up, but we don't want to make that setup right now, so for now as reference just drop down another transform node, put it before the rising up transform. Let's also rename this to rise up anim, and this will be scale anim. So after the rise, I want this to scale up to the maximum value, so let's put a keyframe at frame 50 on the universe scale, and we want this to be at the maximum, let's say at 105, so let's set it to 6. Put a keyframe, and then we will have some camera movement, and let's say on frame 200 it will start to shrink back again until 225 we will be back to 1. Now the core should fall on the ground, but we actually want to split our geometry here. From this frame we want to switch to another setup where we can dynamically simulate the falling of the core on the rock. So let's plug a couple of null here, one at the end. We will call it out core start, and another null we want to place it after the source geometry. We will call this out core. Now go back, we want to mark this as green and call it core start. Drop down another geometry, mark this green as well, let's call it core end. Inside we will take an object merge and we will point it to our core start out core. Let's accept it. Drop down another transform node and set it to the y-axis to be 10. So it will match the same position of the core start on frame 225. Now drop down another null, let's call it out core proxy. It will be the geometry we will use for the simulation. Let me rearrange those nodes. Now let's create a DOP-net. A DOP network is the network where you will do all your dynamic operation. So we basically just created our first simulation, even if it's an empty one right now. So if we put the display flag on the DOP-net, let's hide the other object, and I also turned on my real-time toggle. Now, if we play the animation right now, there's a blue bar going on. This is Houdini telling you that what are you seeing is a simulation, and there's files being cached on your RAM's computer. So by default, as you can see, the simulation starts on frame 1. We don't want this, we want to use this network only for the end of our core animation. So on the DOP-net, you have the simulation tab, you can set the start frame. We want to set this as 225. So now there's no simulation happening before that particular frame, and that's exactly what we wanted. Now we can dive inside and start to set up our dynamic network. As you can see, you already have a node inside the DOP-net, it's the output node, and this is what it will be taken out from this network. So for a dynamic simulation, basically all we need is an object and a solver. The solver depends on what you need to simulate. If it's a pyro, it will be a pyro solver. In this case, we need a rigid body solver, so let's take one and plug it to our output. As you can see, you have a bunch of parameters in here, but the simulation will be really simple and all the default setting of the solver will be fine for now. For the object, what we want is an RBD object. We want to plug it to the first input of the solver. As you can see, it has the label object. And for the object, we need to change the subpath to the out proxy we created before. So let's accept it. Now, if we go on the first frame of our simulation, you can see that we have the object, and if we play it, nothing happened, because we don't have any force or velocity in here yet. So first thing, we need gravity, so let's take a gravity force node and plug it after the rigid body solver. Now, if we play it, we will see the core falling. Now we need the core to collide with the rock, and to create collision, we need a static object, because the rock will be a static one, and a merge node. The merge node inside the DOP-net, it works differently from the classic merge node you have in SOP level. As you can read, the left inputs plugged on the merge node will affect the right inputs. So we plug the static object, meaning our rock, to the left input, and the gravity on the right. So the rock will affect the core falling, and we want to plug the merge result inside the output. Of course, for now nothing will happen because we didn't set the static object itself. The thing is, we don't want to use this whole geometry for the simulation. It will be a waste because the collision is happening only on the top part. So inside the rock RNDR node, after the transform, let's plug a clip node so we can clip most of this rock. Let's increase the origin y-axis to something like let's say 3.8. After the clip, let's create a null and call it out collision geo. Now let's go back inside the .NET, and in here where it says SOPAT, plug the rock RNDR out collision geo and accept it. Now if we play it, we have collision, but if we zoom in, you can see that the collision are not accurate at all. And this is because we still need to set some things in our RBD stuff. So first, going on the RBD object, let's turn off display geometry, and on the collision tab, let's enable the collision guide, so we can see that the shape that is actually taking care of the collision is not that detailed as the original shape. So we can increase the uniform division to something like 100. And by going on the first frame, you can see that now we have a more precise shape for our core. So let's hide the guide, display the geometry, and hit play again to see what we have. So nothing seems really changed, and that is because we still need to take care of the shape of our rock. So by going on the static object node, hide the geometry with display geometry off, and on the collision tab, activate the show guide geometry here on the bullet data. And as you can see, the shape that is taking into account the collision is not actually resembling our rock. As you can see, it's a low poly version of our source geometry. We can change this by changing the geometry representation from convex hull to concave. In this way, it will match roughly the original shape, and go back to 225 and hide the geometry. Now the collision shape is basically the same as the original shape, so let's hide the collision guide, display the geometry, and hit play. Now, as you can see, we have a much more accurate result. And even if for this case it can be perfectly fine to use this kind of setup, I want to show you how to use RBD solver instead of bullet data, because when it comes to really complex shape where you want to have collision, it's a good idea to switch to RBD solver, and I will show you why in a second. Basically, the way Bullet Engine works, it takes your original shape and it tries to replicate it by using some basic shapes like boxes, sphere, a plane, or more complex one if you set it to something like concave. And it works fine if you have, large scale simulations, so you don't see the collision from very close, or you just need simple collision. But when you will have more complex simulation where you have, multiple animated objects colliding with complicated shape, you will really want to switch to RBD solver. That's because RBD solver is capable of using volumetric data. That means we can use VDB to create our collision shape, and that's way more efficient. So first we need to create our volumetric data. So let's go into the rocks RNDR node, and let's branch out after the polyfill. So we want to create a VDB from polygon, plug it to the polyfill, and let's set it to 0.02. We will end up with a volume, and now we can create another null, and let's call it out collision SDF. Now go back to the dynamic simulation, so core end, and inside the .NET. In here, let's hide the guide geometry for the bullet engine, and let's enable the one for the RBD solver inside the volume tab. By default, basically is taking the original shape, so the one coming from out collision geo, and it tries to replicate it with this uniform division parameter. If we increase this, you can see that the shape is going to be more precise, but that's not how we want to use it. We want to change the mode from ray intersect to volume sample. And below we should have the proxy volume channel where we can plug the new volume we created. So rock, R&DR, out collision SDF. We can leave the original shape here. This is just for the display when we check display geometry. But now, as you can see, for the collision volume, we are using that BDB shape we created. So let's hide it and display the geometry so we can see the original shape. And on the solver, we need to change the solver engine from bullet to RBD. So let's see it play. And as you can see, it works perfectly fine. Even if in this case, it doesn't make so much of a difference switching from RBD or bullet. Now you know how to deal with both of those. So we took care of the collision, but now we want to tweak the simulation itself, because right now the core is falling straight down on the rock. And if you watch the final animation, we are coming from a situation where we have this closing in animation. So before the fall, what I want to add is some motion to add something like a knockback effect on the core to make it move on the rock and also rotate it a little bit during the fall. So first we want to take care of some of the physical properties of our object. On your RBD object, if you go on the physical tab, you have all the parameters you need to tweak the physical values of the object, like the density, the bounciness, the friction. Now, I will leave the mass to be computed automatically and also the density as the default value. For my values, I just want to change the bounciness, meaning the elasticity of the object, to 0.226 and the friction to 3.28. Again, this is just the values that I have from my final scene. You can tweak your values as much as you want until you have something that suits you. Also, you have the physical property, of course, also on the static object, but for this kind of simulation, we just want to leave it as the default value. So now let's see what we have. Alright, I'm good with the physical properties. Now what I want to add is that little bit of motion to create something like a knockback effect. And we can do it here on the initial state. We can input some values for the initial velocity and angular velocity for our object. But before doing that, let's do another thing. If you click here, if you press and then choose this flipbook with new setting, we can create a flipbook so we can have an idea in real time of what this animation looked like until so far. So let's leave the sides. Let's see, let's put it to full HD like our camera. And we want this to be from 225 to the end. And let's hit start. So Houdini will generate a flipbook animation for it, and let's wait until it finishes. Alright, so if we play it, I can already see something I don't like with the falling, because it seems the core is too light so far. And since we have just one object, and we really don't care about the physical accuracy of the overall simulation, we can actually tweak the gravity force itself. Right now is negative 9.8, which is the correct physical values of the gravity. So let's say we want to put it to minus 20. Let's quickly do another flipbook. And let's see how did it change our simulation. And let's see, yeah, it's way better right now. So to add the initial motion to this object, we can do it here, as we said, in the initial state. What we want to add to this object is some velocity to a certain direction and also some angular velocity to give him some spin. So our camera will be oriented roughly like this, meaning we want the core to move to the other side. So let's say we want to move it in the negative z-axis and in the negative x-axis. So if we add some value to the z-axis like -5 and plate, you can see that now the object has a little bit of a push towards that direction. And I already know that the value I want to set is -3.8 on the z-axis and -1.8 to the x-axis. So let's go to the top view and plate. So now the direction is good. I wanted to move a little further away, so I want to also add some velocity in the y-axis. So it will have some little jump effect when we start the simulation. So let's set 2 on the y-axis, and let's also see it. Now we want to add some rotation on it. And for the values, I want to set the x-axis to -80 and the z-axis to 120. So now, just for explanation, I will set the velocity back to 0. And as you can see, by increasing the angular velocity, we added some rotation to it. Now I will go back until I have all my values set, so the combination of this value will be something like this. So we have the core that is closing and is being pushed away a little bit from the camera. And that's exactly what we're looking for. Now let's go outside our DOPNet and drop down a DOP import node. This is the node you are going to use to extract information and data from your DOP network. So let's select it. And here on the DOP network, we want to put the DOP network where our simulation is. As for the object mask, we actually want to use the name of the object we want to take out. If we go back inside, you can see that this object is called RBD object 1. So here we can type star RBD star. So it will take every object that has this RBD sequence in its name. For the import style, we could do fetch geometry from DOP network. This will take out the entire object from the simulation network. But what we want to do is to create points to represent object. In this way, just a single point will be created from our simulation network. So we can use a copy to points, and we plug the resulting point from the DOP import to the second input of the copy to points. And for now, we will plug the core proxy we use for the simulation in the left input. Later on, we will replace it with the high definition mesh of the core. So on the copy to points, we're now using the simulated point to copy our geometry. So now let's drop down a null after it and mark it with green and call it out core end. So now we have both of our animation for the core, the end one and the start one in here. Let's mark this green also. Now we can merge those two, and we want to create another geometry. This will be marked as black, so we will use this for render and call it core RNDR. Let's dive inside, and in here we want to use two object merge, one for the core start, and we will take this out core start, and another one, let's just duplicate those, and we will take out core end. So we want to use a switch node, so we can switch from the first one to the second one at frame 225. And to do this, just on the parameter where you can set the input of your switch, we can type at frame is greater than 225. Let's drop down a null after this, and let's call it out core render. So now we have our initial animation. It will close, and then it will switch to the simulated one. So now that we have our full core animation from the start to the end, we can actually lay down our camera animation. So go back outside, and we don't want to display the green nodes, and go back inside the rock RNDR because we don't want to have the SDF or the collision geo visible outside. We want a new null, let's call it out rocks RNDR, and this will be visible. So now go back outside and create our camera animation. So let's drop down another camera. I will rename the cam1 as the cam test, and this will be our main camera. So let's rename it and set it as Full HD. Now what we want to do is to create a simple camera rig to have the translation and rotation control and also another independent control for the zoom effect. To do that, just drop down a null, we will call this aim and connect it to the camera. Let's hide those geometry for a second. By connecting the null to the camera, what we created is basically a parent constraint. So now if we move or rotate the null, also the camera will be affected. So we can control translation and rotation, but on the camera we still have our z-axis. So with this one we have an independent control for the zoom effect. So let's create our camera animation. We want this to be displayed on the viewport. And I already know that the initial value I want for the zoom will be 6, so I will set it as 6 for now. Also, I want to split this viewport left and right, so I can have my main camera on the left and some perspective view on the right. So I will put my final values here for the camera animation. You are free to follow those values or create some variation on your own. So it's 0.017, 5.1, and 0.03 for the z-axis. So I'm moving the aim and so the camera as well. For the rotation, it will be negative 30.9, negative 1.9, and 0. So this will be my initial view, and also I want to lower the focal length of my camera to something like 30 millimeter. So I will set a keyframe on frame 5 right after the core is start to rise, and we want to follow it with the camera. So let's say on frame 45 we are moving up until, let's say, 9.9. Also, let's tweak these values a little bit so it won't be a perfectly straight rise for the camera, and put a keyframe. Here the core will open, so it's the moment where we want to use the zooming effect. So on the camera, let's say on frame 50, we will have that value of 6, and let's say on frame 19, we reach the full expansion of our core, so we will put this as 9.2. Then the core will stays open for a little bit. We will add some movement to our aim, but let's first set the zoom effect back, because on frame 200 the core will shrink back again. So let's put a keyframe on 200, and let's say on 230 it will be 6 again, so we zoom back on the core. So back to the aim, we want to create some rotation during the time the core will be open. So let's say on frame 230 we will increase the Y rotation to 36.8, put a keyframe. So now it will rotate during the opening part, and also let's slightly change those values for the translation. So 0.06, 10, and 0.08. This is just to create some minor variation during the other transformation on the scene. Now the core will start to fall, and we want to follow it with our aim. So on frame 250, let's follow it with the camera, and let's put -0.2 for the z-axis, let's decrease the y-axis until 5.55, and also we want to move the z-axis, so let's put -3. Keyframe the translation, and we won't edit the rotation on this keyframe, so the core will fall and the aim is following it. Moving on, the core movement will roughly stop at frame 300, so we want to set our final translation keyframe on frame 300, and we want to follow the core even more, so let's say 5.2, but we want to center it a little bit better, so go, let's say -3.5, and maybe a little closer, so -7, and set a keyframe. So now we are continuing to follow the core until it stops. And maybe on frame 250, let's center it back a little bit better. So move slightly on the x-axis. And when you edit a value that it has already a keyframe on that particular frame, you don't need to set a keyframe another time. So now we want to basically continue this rotation movement, and we want to be as smooth as possible. So let's place the timeline on the last frame of our animation, and we want to set the x-axis to -41.7, 65 for the y-axis, and -12.8 for the z-axis. So here we are rotating with our camera, and now when we fall, the rotation is continuing the movement in a smooth way. So let's close this, and we want to create a flipbook to see what we get. And this time we want the frame start to be 1, or you can put back the variable rf start. So let's start our flipbook and let's see what we have. So I'm pretty happy for the time being with the result. Maybe we will tweak the animation curve of our camera animation, and we will add some variation to the core. We will add some noise to it, but for the time being, this is just what we wanted. We have a basic camera animation, so now we can finally dress up our scene with the other rocks and the following environment.